Adventure.
Yeah.
Okay. Hi everyone. Thanks for joining us for another episode, another season, who knows, of the Formal Demography Working Group. If you're new here, I'm Monica Alexander. I co-organize this with Vanessa DeLago, and also our newly appointed co-organizer is Antonino Polizzi. And so we're sort of all over the world, but have a shared interest in formal demography and trying to sort of get, get people more interested in it and hear some recent work. So today we're really excited to have Nick Vandervoort speaking to us. Nick is a second year PhD student in sociology and demography at the University of California, Berkeley. He comes from a very interesting background, double majoring in physics and sociology in undergrad from UCLA. And he now works with Josh Goldstein on something that we'll be hearing about today. And he's also more broadly interested in other demographic issues around fertility policy and things like that. So, thanks very much, Nick, for agreeing to speak to us today. Really excited for your talk. Um, if it's okay, we'll have sort of major questions at the end, but assuming it's all right with Nick, we can have some clarifying questions during the presentation. Thanks.
Yeah, then that sounds great for clarifying questions. And thank you for the introduction, Monica. And I'm really excited to be here. I was just saying before the talk that I actually had no idea this group existed before Antonino emailed me. So yeah, I'm happy to be here and looking forward to sort of sharing this work and having a good conversation. And yeah, I just want to acknowledge that this is with sort of Josh Goldstein, who many of you probably know. And this work is actually coming out of a mathematical demography class that he taught last year and I took. And this was the sort of term project, and it's evolved since then. So it's really a formal demography project from the beginning. And so yeah, today I'm going to be talking about population momentum from replacement migration, and I think really quickly, I just want to caveat or acknowledge that, as kind of often happens with formal demography, a lot of things are being kind of bracketed. And so in the background, there's really a lot of like policy conversations, sociology of migration, sociology of reproduction and gender that I think in a lot of this talk, I'm going to be skimming right over because there's a lot of formal demography to get to, and that's kind of the namesake of the group. But I sort of want that to be, I don't know, I want us to maybe keep that in the back of our minds and maybe we can return to it later on. Okay, so with that out of the way, I will get into it. So I'll talk about the agenda for a moment. So first, I'm going to spend a little bit of time talking about what population momentum is, even though I'm sure most people here have heard of it or maybe know it intimately. It'll be good to have a little bit of a refresher and sort of look at the classic case that Kiefert's laid out with sort of a fertility transition. And that's going to sort of set the stage for the main comparison to the centerpiece of this talk, which is a replacement migration scenario. So then I'm going to preview the results for a little bit. Afterward, I'm going to talk about the model. And so that's going to include kind of the analytic formalistic model. And then there's also a simulation component. And in the results section, I'm going to show how those agree with each other, which we're quite happy about. And so we're going to be looking at population size, which is kind of the focus of population momentum, but then also age structure, because not just population size matters, as we all know. Um, and then if there's time, I hope we can get to this sort of more recent work on this, what I'm calling right now the sliding scale, which is something that lets us sort of go between fertility and migration transitions and do sort of any weighting of the two. Okay, and after all that, I will conclude with some thoughts and then look forward to a discussion. Okay, so let's spend a little bit of time talking about just what population momentum is. So Keyfitz has this famous paper where he sort of defined a lot of these things and laid them out. And so we can kind of think about population momentum as a closed, growing or shrinking population. After that population reaches replacement fertility, it will continue to grow or shrink for some time. And that's where the name momentum comes from. It's kind of like even after you take the wind out of the sails, like it keeps going forward, right? The population keeps doing what it was doing. And so here on the right, I just have the sort of an example of the female population of Japan. And so this is normalized to be 1 in 2023 on the y-axis. That's just population size. And then we have the year on the x-axis. And so right at this dotted line where we assume the population was shrinking stably beforehand, which I know is an assumption, but we'll talk more about that. We just pretend, or we assume that at 2023, the population reaches replacement fertility. So 2.1 kids, whatever, or around then, whatever it looks like. But we can see that even after you do this, the population shrinks for some time, and the shrinkage can be pretty dramatic. So here we start, if this happened at 1 million people in 2023, you would end at 600,000 approximately, which is a pretty big difference. And so population momentum has kind of blossomed into this literature with extensions, and the UN does yearly projections for like countries around the world. And so there's a lot of interest broadly in like this phenomenon, even though it's kind of this like idealized scenario. And here I just wanted to also flag that I'm gonna return to like using Japan as an example for most of the talk, just as something to sort of hang our hats on, but then later I'll do a bit of international comparison as well. Okay, so a little bit more on what population momentum is, and then we'll move on. But the mathematical definition is the ratio of the final population to the initial population. So in this case, the momentum would be about zero point 0.6. And can you guys see my mouse as I move around? Yeah, okay. So we can see that, for example, at the end here where I'm circling, the population ends at about zero point 0.6 on this sort of relative scale. And we started at like 1.0 by construction. And so if we sort of do zero point 0.6 over 1, we get zero point 0.6. And that's what you would say the momentum is mathematically here. Um, and that's also why it's all right to do this sort of like normalization on the y-axis for population size, because if you had this all in a bigger scale and it was millions of people, you would get the same ratio, right? So this is sort of a way to help us like understand what's happening and just simplify our axes. Okay, and the last thing I want to touch on is that key fits in that paper I mentioned on the last slide also derived this kind of famous expression, at least, well, I don't know, famous within formal demography maybe, um, of uh, what the result of this mathematical momentum will be for a population that if it were to undergo this like fertility transition. And so this is all like aspects of the initial stable population. So we can see, for example, that life expectancy matters, the crude birth rate matters, the growth rate matters, the mean age of childbearing matters, and the net replacement ratio matters. And so this is interesting, I think, for two reasons I want to flag. So one is that we can actually just use this formula to say like, okay, what will the momentum be, right? And the other is that you can actually look at sort of what's in this expression to like think mechanically, like what matters for population momentum, like what is going on sort of under the hood. And as I'll show you in later slides, I want to do something similar for the migration case. And then we can, also take those two sort of paths to say, okay, what actually happens to the momentum on one hand, and then on the other hand, what is actually driving this under the hood? And the sort of formal expression is a great way to, I think, to kind of get a handle on that. Okay, so this is sort of like classic population momentum with the replacement fertility. Now I'm going to preview the main results from this work, which is that you can see I've added this purple line here, which is the replacement migration line. And so what happens here is that in 2023, we can think instead of changing fertility rates to enforce long-term like stationarity where the population doesn't change, you change migration rates to get the same outcome. And so I haven't told you how we've done that because there's a couple different ways to do it. Um, and I'll sort of do that later. But the main result that I want to share here and the main takeaway is that it produces less momentum, right? And you can see that sort of the population was shrinking, it shrinks less for replacement migrations. That's what I mean. And the reason I have a star here is that because if you were actually going by the mathematical definition, you would have to flip this for this case because you actually end with a greater population. But I kind of want to think about momentum intuitively, as in like if the population is shrinking, it'll shrink less in the migration case. If it was growing, it will grow less in the migration case compared to the sort of classic fertility case. Okay, so I hope that makes sense. And I know that's like a little bit of a confusing switch, but I'm just kind of trying to think about momentum intuitively, and sort of going back to like, a ball that like, I don't know, you stop pushing and it keeps going a little bit, right? Okay, so how can we understand this, like these results? So what I want to do is unpack this phenomenon with some simplifying assumptions that I'm going to go through one by one. So the first is I just have stable population theory, but what I mean is that we're assuming that populations are stable beforehand, which is kind of a somewhat common assumption in this literature, but there's also work on non-stable momentum, and that's a possible extension, and we can talk about it later. I'm also going to assume that the populations are initially closed. So even though we're going to like open them to in-migration or out-migration, depending on whether they're growing or shrinking, we're going to assume that there's no migration to begin with. Also not a realistic assumption, right? But it's one that sort of we work with here, and we can talk about more later on. And then lastly, I'm going to assume that migrants experience the same demographic rates as everyone else. Pretty much every time I've like talked about this work, someone suggests like, oh, but don't you know that migrants experience different rates and all this? And like, yes, we do know about that, but it's kind of a whole, I mean, it's always a trade-off between sort of interpretability and realism, right? And so having sort of two different projection groups for migrants and non-migrants is really kind of a whole other thing. And even there, you're missing heterogeneity. So for now, we don't do any of these things, but they're all possible extensions, and we can talk about them more later. Okay, so with these assumptions, I want to go through first an analytic solution and then talk about the simulation. And so I want to show that we can find agreement between these two things, which makes us confident that both of these are capturing the sort of dynamics that we want them to. Um, and then with the analytic solution, which is sort of like that key fits expression, this like equation of like what actually determines momentum numerically, we can sort of from that extract the components of momentum due to replacement migration. And then on the other hand, with the simulation, that will allow us to look at sort of more temporal dynamics, look at things like age structure, like what would the population look like if this happened, as opposed to just what's sort of the mechanics driving it. And so I think these two sort of ways of approaching the problem both like give us different angles into the phenomenon that we're trying to understand. Okay, so I'm going to start with the analytic piece, and so I'll go into it now. Okay, and so I wanted to flag here that in theory we could use any migration schedule, and by migration schedule I just mean the ages at which migrants are arriving. And so this is a very like formal demography way to think about it, but in the fertility case, everyone is like arriving into the population at age 0 because these are newborns. But if you're thinking about migration, you could have people coming in at all different ages. You could have everyone arriving at age 20, right? I mean, you could simulate anything. So in theory, you could use any migration schedule. Here we're going to use a schedule from Rogers Castro from a paper a couple decades ago, just for comparison. And it looks like this. And so this is not meant to be a migration schedule that like represents all countries, um, but it is sort of one that has some empirical grounding in the literature and a schedule that we're going to use just so we're holding that constant for the analysis and the comparison. And when we do an international case later, we're going to just use this migration schedule because you can use each country's own migration schedule and then scale it up or down, but then you have so many things changing at once, it's sort of hard to see what's happening. And so here we're going to use this migration schedule, and we also think it's kind of sufficiently complicated to be interesting. It's not just like some, I don't know, like normal distribution or something. You kind of have these two peaks. Uh, and so, yeah, that's what we're using here. But again, this is something we can change in the model and something we can talk about later. And then fertility and mortality data are coming from the UN Population Division. And then everything you're seeing is from all the fertility mortality data are just from the year 2023. Okay. So how do we actually model this? So following some work from Alho, we're going to use what's called the migration survivor function. And here we're diving into some formal demography. So bear with me for a little bit, but there is some intuition here. So this function g of x is called a migration survivor function. And what is it doing? What is the integral doing? So we can basically think of for any age x, we're summing the migrants who arrived at younger ages and survived to x. So that's what this integral is doing. So for example, if x is 20, I'm going to go through ages 0, 1, 2, 3, 4, 5, etc., and say how many people were arriving at each of those ages. This is just the migration schedule. And then how many people who arrived at age 0 survived to age 20, how many people who arrived at age 1 survived to age 20, and so on. Um, and so what this ends up looking like is a curve that's more like this. And so we're going right from this migration schedule, just who's arriving at each ages, to who ends up sort of existing in the population at each age. And so it's kind of like surviving the migrants forward in time, in age and time. And that's why it's called the migration survivor function. And so I know this is like maybe a little strange, especially if you haven't seen a ton of formal demography before, but hopefully there's intuition for this. And if not, we can always sort of go back and discuss this more. But I'll talk about it a bit more on the next slide too. So how can I want to ask this question, how can we combine like regular survivorship and migration survivorship? And in this following this Alho paper that I talked about on the last slide, you can kind of just add them together. And I'll talk about the C parameter in a minute. And so what this looks like here on the right is you have, so we can start with this sort of black curve, which is just a classic survivorship over time. You have age on the x-axis and proportion surviving on the y-axis. And so we can just see that over time, you start with everyone surviving and eventually the population tapers off. And I'm going to show here that if you just add this sort of migration survivorship to the classic survivorship, you get this migration inclusive survivorship curve, which is this pi of x like term here we've defined. And so this is not a traditional survivorship term, right? It's not monotonically decreasing like this black curve is. This is how most survivorship curves look. But you actually, start with some number of newborns, and as they age, you get more people. And so from the cohort perspective, as people are aging in the population, they're sort of sponsoring migrants into the population. And again, this is not meant to be a totally realistic one-to-one match of how migration actually works, but it's a way to sort of formalize migration in order to sort of have it slot into formal demography and like renewal theory that we can then take advantage of. So this is a bit of what's going on under the hood. We're using like this migration inclusive survivorship concept. And then this parameter C here, you might have been wondering what that does. It basically will scale this g of x term up or down. So you can think of this purple piece kind of sliding up or down in relation to this LX piece. And that's going to kind of control how much migration is happening. If you need more migration, you can make C bigger. If you want less, you can make it smaller. If you want out migration, then C becomes negative, and so on. And I'll talk a bit more about this going forward. So how do we get to replacement migration? Well, we're going to start with a stable population, like I said earlier, and we're going to satisfy the classic Euler-Lotka equation, which anyone who had to put in the passcode for the Zoom knows a little bit about. Um, so this is like the population before we do anything, right? This sort of stable counterfactual. We have an intrinsic growth rate R, X is age, F of X are fertility rates, and L of X is this classic survivorship. And then we want to transition to a stationary population, long-term stationary. And instead of R satisfying Lotka's equation, we actually want C to satisfy this sort of modified Lotka's equation, where a couple of things change going from this first to the second. So this exponential term goes to 1 because R is 0. We're going to enforce the R is 0 because we don't want the population to grow anymore. Um, and we're going to keep the sort of fertility rates the same. We're not changing those at all. And we're replacing this classic survivorship term with this migration inclusive survivorship. And so now we're going to say, okay, what does this migration inclusive survivorship need to be, where C is the only thing that's a variable in order to satisfy this equation? And if this isn't making 100% sense, I think that's okay. But also feel free to ask questions. But there's kind of a lot going on under the hood here, and I don't want to get too bogged down in it. So hopefully the intuition is there. So from what I've just laid out, we can actually derive this long-term stationarity condition, and it's not too important to like really dig into what these integrals are here. But what I'm trying to show here is that you can write down like, okay, C has to be like this exact thing. You can say like, we can figure out what number C has to be in order for the population to be stationary in the long run. Just like how when Kivitz derived this, he sort of showed that if you divide the fertility schedule by the NRR, then you have the sort of new fertility rates that you need for the population to be stationary. So again, I'm kind of going to skip over. I'm not going to really interpret what these are right now. We can come back to it if we want, but I just want to flag that this is kind of the path we're taking. Okay. And so I'm going to skip a lot of the mathematical details in between, but you can actually derive this super elegant, just like concise key-fits-like expression for momentum, and I'll show you it right here. And so that was a total lie. It's like kind of a nightmare. So it's not elegant at all. And I think I don't want to, again, so I haven't defined a lot of these terms, and that's okay. I just kind of want to point out that yes, we can write out this expression, but it's this nightmarish thing. It's not very interpretable. And so I want to return to this expression later and sort of maybe see how we can piece it apart and make some more sense of it. But for now, I think one thing I want to flag is that migration is really complicated. And I think I've heard a demographer in a talk recently say that migration was like, I don't know, like the adopted child of demography or something. And it does, I think you see that come up in all sorts of places when people try to incorporate migration into these models. And you get like results like this, which are really hard to make work, but I still think there's a lot of sort of analytic value in attempting it. Okay, well, I'm getting off track, but with that out of the way, and again, I'm going to return to this expression later. I just want to show for now that, you can follow this all the way down and do this analytically, and you can see what the expression is. So now I want to show you how this expression that I just showed you, even though it looks nightmarish, we're pretty confident in because it agrees with simulation results. So here I have four countries just chosen because they roughly had different NRRs in 2023. So I have Japan, Brazil, Algeria, and Nigeria. And NRR, if you haven't seen that term, it basically you can think of it as if the NRR is less than one, the population is shrinking, and if the NRR is greater than one, the population is growing. And so this middle column here of this middle column here of analytic is from the expression I just showed you, and then MSIM is from the simulation. And so we can see that there is pretty good agreement in every case. Uh, this gap is just like the math, just like the difference between them. It's not a ratio, it's just the difference. And we can see that the gap is on the order of like 0.02, 0.045, etc. So there's a pretty good agreement. It's not perfect, but sort of for showing qualitative results, it's quite good. And so we're pretty confident from this that the formalism and the simulation are capturing the dynamics that we want them to. And one thing that I've kind of noticed while testing this is that the agreement is somewhat better for lower growth rates, as we can see by the gap kind of getting bigger as we go to higher growth rates, as we sort of go down this column. But again, even in a case like Nigeria, where the population is going really quickly, the gap isn't so large. So we're not really convinced, or we're not really worried that anything is fundamentally broken here. But there's always going to be issues with sort of making a continuous process discrete in simulation and so on. Okay, so now I'm going to talk about some results. So this is kind of the result I showed you guys at the beginning of the talk about population size. And so I want to kind of return to it, having shown you a bit more of what's going on like under the hood with the formalism. And so what I actually want to say is that population size, at least in this case, is somewhat straightforward. We can kind of see that both of these paths, kind of the replacement migration, the replacement fertility case, follow a kind of similar trajectory, just that like the replacement fertility trajectory is more pronounced than the one for replacement migration. And so what I want to use this as kind of a jumping off point to look at the age structure. Because one thing we really care about for momentum is population size, of course, and that is hugely important for a lot of policy and other considerations. But if you're thinking about something like Social Security payouts, right, what you really want to know is the age structure. It's how many old people, young people, working age people are there. So I want to turn to those results next. And so what I'm showing you here are the stable and stationary age structures for this Japan case that we've been talking about. So we have age on the x-axis and then sort of the like proportion, the fractional contribution of that age to the total population on the y-axis. So if we start with this black curve, which is the original stable age structure, we can see that this is kind of the classic age structure of a shrinking population, where you have the fewest sort of people at the beginning, and then you have this spike at old age, and then everyone has to die eventually. So you have this big kind of skewed peak over here. And this plot is normalized so that the original stable population sums to one. So we can see kind of immediately that the fertility and migration cases, they have less total population because if you sum up the area underneath, it'll be smaller than this area under the black curve. And that sort of aligns with these results. But then also, if we look just from like at the actual age structures, we can see a couple of interesting things. So one thing that's interesting is that this fertility case actually has the smallest total population size at the end, but you actually have the largest number of births per year, which you can see as like the highest level on this like sort of at the zero age, right? And that's sort of a result that Kiefert's found in the original paper, but we sort of see a continuation of it here with the migration case, which is kind of interesting. Um, and part of that is because with the migration case, you're adding people uh, at sort of more middling ages, right? But if you look at the fertility case, you're adding people at age zero. So that's kind of where like this fundamental difference comes in. And so these are interesting results, but at the end of the day, what we're looking at here is sort of the original stable age distribution and then the final stationary age distributions of these cases. But this is like, after all the dust has settled, potentially hundreds of years into the future. So what I want to ask next is how does age structure change over time? And the way I'm going to look at this is with dependency ratios. So I'm going to start, there's three. I'm going to walk through each of them in turn. But the young dependency ratio is the fraction of the population aged 0 to 14 over 15 to 64. And so it kind of speaks for itself, right? But you generally want, I mean, want is kind of subjective, and I'll talk about that later. But it's generally thought to be good to have like lower dependency ratios, because then you have sort of more working age people to like support the young, and then later we'll look at the elderly. So these are the results for these different scenarios over time. We can see that in both cases, you start with a really low dependency ratio, reflecting sort of Japan's like aged population structure, where there's not a lot of young people. And then immediately both of them like shoot way up, right? With the purple migration case and with the red fertility case. And this is because you're adding a lot of people at the younger ages, right? While the older ages are sort of hollowing out. But then what we see next is that in the long run, migration has fewer births and this larger middle-aged population because in the migration case, we're adding a lot of people into those middle ages. So that's going to bring the young dependency ratio way down, whereas you don't really see that in the fertility case. And then you also have these sort of oscillations, which are sort of an artifact of the way Kiefert's momentum works, where it's kind of this weird thing where you start, you change your fertility rates, and it kind of takes a generation for that to show up in the next generation of people who are having kids and so on. So you kind of get this like wave-like effect where you eventually converge on some number. And so this is years. And so even at like 200 years, we're not at the stationary state. So that's why it's important to look at these sort of transient temporal dynamics and not just this kind of stationary cases like I was showing you in the previous slide. Okay, so this is the young dependency ratio. Let's take a look at the old age dependency ratio. So this is the fraction of the population aged 65 plus over 15 to 64. So this is kind of like how many like elderly people are there relative to working age people, like very roughly. And so again, another important marker for policy, especially if you're interested in something like Social Security payouts, for example. And so again, in both cases, we can see this drop, and there's a little bit of like no effect at the beginning for the fertility situation, and that makes sense because until 15 years, there shouldn't be any change, right? Because all the changes happening with like the newborns. But we see both drop kind of precipitously, but migration drops quicker and lower. And the reason for this is that you're adding like all these people into the working age population. Like most migrants are arriving like in this denominator and then like aging in this denominator for some period of time. And then eventually they actually switch like a large time in the future. And this is actually a pretty curious result to me. And again, it's like varying levels of realism here. This is like 200 years if everything stays the same. So obviously it's not super realistic, but it is kind of interesting that in theory you have this big gap and then eventually a switch. Um, and so one of the takeaways from this is that the kind of like legacies of thinking about like replacement migration or replacement fertility are pretty long. And if you actually want to like use these insights for policy, it's going to really vary depending on what time scale you're looking at. And yeah, I think that's all I want to say about this for now. And now I'm going to show you the total dependency ratio, which you can think of as just the sum of the old and young dependency ratios, right? So it's how many people are there aged 0 to 14, plus how many people are there 65 plus, and then a big sort of line, and then in the denominator, you have 15 to 65, like the working age population. Um, and this is literally just the sum of the previous two curves I showed you, just put on one plot. So, and like I said, uh, usually you kind of want less dependency. That's like usually portrayed as like something that's better. I don't want to say that this is like always the case, that it's always like bad to have like a bunch of young people and old people or something like that. Um, but for a lot of policy considerations, you do want less dependency, and you can see here that migration implies a much more favorable age structure on this sort of like interpretation of dependency, especially in the short term. So we start with pretty high dependence in both cases, and this is because, again, in the stable case and the stable counterfactual, Japan has this really large population of like older people because of its like low fertility. And then in the migration case, we see this like huge drop in dependency that persists for quite some time. And even like farther on, I mean, both of these cases are sort of like you could be construed as favorable to the dependency ratio because you end like lower than you started. But if we're comparing the two, and if a policymaker were comparing these two, there are still like really significant differences between these two, especially in the short term. Um, okay, so before going into the next section, I might pause and see if there's any questions because I know this has kind of been a lot of material. I've been going kind of quickly. So, yeah, are there any like clarifying questions or anything that would be helpful for me to go back and sort of go over again? And if not, that's okay
Hi,
too.
hello, my name is Andrea. Can
Hi.
I have just a question quickly?
Yeah.
So how, like in your migration survivorship curve, you are defining non-survivors as immigrants and those who died, right?
Yeah, let me just go back to this. So you mean this curve, right?
Yeah, so your non-survivors for the migration survivorship are those who emigrate and die.
Um, yeah, so like in this case, it would just like decreases would just be those who like that would just be death. Because people are only entering the population. Like there's, I mean, at least like in theory, there's like no outmigration happening in this case. But if you had a growing population, which I'm not showing here because of because of kind of what you're alluding to in this question, because it gets really strange, then you would have outmigration, and then it becomes kind of strange to like interpret what is outmigration and what is like death, right? What does exiting the population mean? Um, so yeah, I think there's a little bit of like ambiguity if we're just looking at the math, and that's totally like right that you picked up on that. But we can always sort of go back to this equation that I'm circling here and like in the like in R and like see like what's like actually happening. But it's totally true that these things are like being a little bit conflated in this model.
Okay, thanks for the clarification.
Yeah, thanks for the question.
Hi, I also have a question.
Hi.
Hi, Nick. I wanted to know, and sorry, I wasn't here at the beginning. Maybe you said this, but I'm curious. Did you talk about, how many migrants? Because I saw the schedule, schedule, but what about the number of migrants entering? Is it the same, like the same number all every year, or? And again, sorry if you said
Yeah.
this at the beginning.
Yeah, I don't think I was super clear on that, and that's a great question. So this is the migration schedule we're using, and for now we have it just sort of being imposed like the same migration schedule every year, so the same number of migrants entering every year at every age. So it's definitely a simplification, um, and kind of a big assumption we're making, and we haven't really experimented with like a changing migration schedule. But I mean, if that's what you're suggesting, and that I think that
No,
could be
I'm just asking what are your assumptions? I'm not suggesting, yeah.
okay.
Just
Okay,
wanted to make sure I understand.
I'll get the
Thank you very
suggestion.
much. Thank you. Yeah.
Thank you.
Hey, Nick, another
Hi.
question.
Yeah.
Feel free to say this isn't clarifying enough. But could I ask you to say a little bit more about what your intuitions are on the long-term trend in the old age dependency ratio? Because that is a head scratcher for me. Because I guess it's not I know, because of the time scale, like it's not the aging of the migrants, like
Mhm.
the migrants who enter. like it has to be something about like the longer term thing that happens like in the next generation.
Yeah, no, I think that's a great question. And I'm going to try to answer it, but I don't think I have a complete answer just to say that right now. These are kind of new results that we're still trying to wrap our heads around ourselves. I think part of what's going on is that there's two things happening. So one of them is kind of like you said, this generational thing of migrants are entering the population and then aging. And so we're sort of going from that migration schedule to that migration survivorship, which takes some time to like reach that migration survivorship stable function. And then while that's happening, like migrants are like having kids and like starting families, right? And those two things are sort of happening at the same time, but they end up, like one will happen a little bit and then the other one will happen. And then I think there's feedback effects going on there. So I think that's why it takes so long for these like forward old age dependency to reach this like actual like level like number. So that's sort of what we're going with right now. But I mean, if you have other ideas or like ways to explore this, I'll definitely be happy to hear them. Yeah.
I was thinking about like it might be helpful to have the visual of what the population pyramid looks like
Right.
at different snapshots in time. Because I, yeah, it's this I find this all really interesting, but it's a little hard to think through
Yeah.
like what it's
I
supposed to look like at the end of the day, right? But maybe that's the key. Something else I was thinking about is the fact that there aren't oscillations in the purple curve here. And
yeah.
I feel like I have an intuition. Oh, well, like I remember from formal demography vaguely why there are oscillations in the red curve, but I was wondering why there aren't in the purple curve.
Yeah, I think that has to do with going back to sort of you can think of like the schedules at which people are entering the population in each case. So like you said with the fertility case, maybe it makes a bit more sense where everyone's entering at age 0 and then those cohorts are going to then go like become parents themselves and you sort of get these waves. And I think in the migration case, you have, at least in the way we've constructed it with the migration schedule we've chosen, the schedule is sort of continuous and like well-defined. I mean, we're doing like a discrete simulation here, but it's relatively continuous, it's relatively smooth, and there's not like sharp breaks. So another situation we've looked at is like what happens if all migrants enter at age like 15 or something, like at the start of childbearing. And I think there you do see like you're more likely to see oscillations. Um, and then that's closer to like the fertility situation, but then you're getting farther away from what migration actually looks like. Um, so yeah, I think it comes down to like the migration schedule that we've chosen here, and that it's a relatively smooth one. Yeah.
Thanks.
Yeah. Okay. If unless there's any other questions, then feel free to interrupt me. I will sort of continue and try to wrap this up soon. So I want to return to that big ugly equation I showed you guys as promised and talk about what I'm calling the sliding scale for a few minutes. So we're going to take inspiration from this paper by Tannen and Espenshade, uh, in a paper they wrote a couple years ago. It was actually an unpublished PAA manuscript that was like almost impossible to find, but that's another story. So we can basically introduce a parameter to weight fertility and migration transitions. And so what do I mean by that? I mean we can introduce this term, we'll call it theta, and theta can range between 0 and 1. And we're going to say that if theta is 0, that's just the classic Keyfitz scenario where we're changing fertility. And if theta is 1, that's going to be the sort of replacement migration case. So 0 is like the red curve I've been showing you this whole time, and 1 is like the purple curve. But with this formulation, we can also be anywhere in between. We can do half and half and be in the middle and sort of do like sort of a half fertility transition, half migration transition, and ensure like mathematically that we're going to have a stationary population at the end. Okay, so why do this? I'm going to show you an even uglier expression before it'll get prettier. So now you can see this is that ugly expression, and I know don't get bogged down in the details. A lot of these terms won't be familiar, but you can notice that there's a couple of thetas here now. And so I'm going to argue that this is ugly, but we can now decompose this expression and compare it to the Keyfitz scenario to get some like theoretical leverage on like what is actually the difference between these two, what's going on mechanically. So we have this ugly expression. And when theta is 0, this reduces exactly to the Keyfitz solution. So that's by construction, right? And that's the one we kind of already knew. But when theta is 1, we have this complicated migration case. So here I put in red all the cases where theta appears, and I'm going to argue that we can use these three instances to actually like kind of draw out three mechanical differences between momentum and the way we formulated it here due to migration, and then momentum due to fertility in the classic key-fit scenario. So below here, I have the classic key-fits result, and then on the top, I have this theta-dependent result. And I know this is a lot, but just bear with me because I think it'll give us some theoretical purchase here. So I think first we can look at how there's this life expectancy term in the key-fit scenario. And in this sort of complicated theta dependent expression, we have this modified life expectancy or adjusted survivorship term, where we can see that we have classic life expectancy plus modified by theta, this migration survivorship-esque term. And so that's sort of like one difference. And then also here in green, matching the mean age of childbearing term down here in the key-fit scenario, we can look at this like modified mean age of childbearing. Um, that sort of depends on a bunch of properties of the migration age distribution in question. For example, this is the difference between the previous mean age of childbearing and the mean age of childbearing of migrants, and then multiplied by this theta term. And if theta is zero, this all drops out and reduces to just the mean age of childbearing. But here you have this adjusted mean age of childbearing. And again, the adjustment is kind of complicated. I don't have all the intuition for it, but broad strokes, we think this is kind of the differences that are coming out. And lastly, we have this other term, this kind of really ugly double integral at the end here that totally drops out when theta is zero. And how we're thinking about this is it's like the discounted or remaining reproductive span of migrants. And so we can sort of see that we're summing over the net maternity function here and also something like the remaining reproductive span of migrants who are entering the population, depending on at what age they are entering. Um, and so again, it makes sense that when theta is zero, and we have the fertility case, like everyone's arriving at age zero. So this term doesn't matter because everyone is sort of going through the full reproductive span, right? Okay, and I know that was a lot, but I'm skipping over details here, but what I want to argue is that momentum due to replacement migration, we can kind of think of it as differing mechanically from the key-fit scenario in three ways. We have this adjusted life expectancy difference, we have this adjusted mean age of childbearing, and then we have this like remaining years of the reproductive span of migrants like effect. And so, and we haven't really hashed all this out yet, but I think in further work, one thing that we could do is sort of decompose these three different things that are going on and these three different kind of deviations from the classic, very well-studied key-fit scenario and get a handle on, okay, when does each of these sort of three different like mechanical effects, like when do they come into play the most? Like maybe it's number three that like matters a lot and the other two not so much, or vice versa. And again, this is sort of new work, and so we haven't really done this, but we think this is one sort of like exciting payoff from actually writing out all the formalism and being to compare between the two cases. Okay, this is kind of a lot on the screen right now. I'm going to walk through what's happening in this figure as sort of an extension of what's happening with this theta parameter. So on the x-axis, we have theta, this sliding scale, right? And when theta is zero, it's the key fits fertility classic scenario. When theta is one, it's totally the migration scenario. But we can also have theta at any level in between. On the y-axis, we just have the momentum outcome as predicted by the equations. And so these countries are kind of, I'm not trying to like match the countries to the colors. I'm just trying to have a bunch of countries for comparison. And again, this is with all the sort of stable and like no migration previously assumptions. So not intending to be totally realistic. But the aim here is to show like graphically that migration produces less momentum because we can see as we move from the left side from the key fit scenario to the migration scenario, we see this sort of convergence, not exactly to one, but like generally to one, where populations are going to be doing less of what they were doing before. And we can sort of see that here. It's a very like consistent result. And so one thing I also want to flag here is that Japan is not a super extreme outlier. I've sort of bolded Japan in purple again down here. I mean, obviously it is like the lowest fertility and the lowest momentum, at least on as we've shown it here. But if you look at like the slope here, like it's not so different from some of the other lines. So I just want to sort of flag this to show that we haven't, and we've chosen an extreme example in some ways for sort of illustrating effects, but it's not a crazy extreme outlier, and everything would change if we chose another country. Um, okay, so we're nearing the end. I want to conclude with some brief points. So our main result is that my replacement migration produces less, with that caveat I mentioned earlier, momentum than replacement fertility. This is true kind of for growing and shrinking populations, as you can see here. Replacement migration also produces a more favorable age structure, with also the caveat that like it kind of depends what you mean by favorable, but I'm sort of taking the dominant policy view here and not necessarily like a moral or normative view. Um, and then also that replacement, so momentum due to replacement migration differs mechanically from Kiepler's momentum in three ways, or we can think about it this way at least. We have sort of a survivorship difference, a mean age of childbearing difference, and then a remaining reproductive span of migrants difference. There's also some extensions we can think about, like we can reconsider some of the assumptions we made in the beginning that we're simplifying. Like we can think about what happens if there was already migration in a population. We can think about what if the population wasn't stable to start with, which is, all these things are going to make it more realistic. But again, there's always this trade-off with interpretability because those horrendous expressions I was showing you earlier are only going to get more so. Um, and then lastly, I think there's definitely um, sort of a lot of work to be done here with linking these results to policy considerations. And there's sort of a lot of discussion of policy in the momentum literature that I think we need to sort of dig into a bit more and see how this fits in. And so yeah, that's all I have for you guys. Thank you so much, and I'm looking forward to the discussion.
Thanks so much, Nick. That was super interesting and really clear. Great presentation. Do people have questions? Either just unmute yourself and go ahead, or in the chat. I have one, but
Yeah.
given that everyone is being quiet, um, and this is a misunderstanding, but with your long extended analytical expression where you sort of you were showing how you would decompose the three different effects,
Mhm.
with your theta involved as well. If you're assuming the same fertility behavior of the migrants,
Yeah.
does the mean age of childbearing and the NRR for the migrants become the same as so do those terms like does mu migrant equal mu then, or is it still different?
It's usually they're usually pretty similar, at least what sort of preliminary looking at them, but they can be different because it'll depend on the migration schedule. Like for
Okay.
example, if you had like all your migrants arriving at like 35, then you'd probably have a really
I
high.
see. Yeah. Okay.
Yeah. And then
Um,
oh, sorry, go ahead.
no. That's
Yeah,
okay.
and then I was gonna say it similarly for like the NRR term.
Yeah.
It's because you have this like, I mean, the fertility is the same, but then you have this survivorship that's changing with this
Yeah.
sort of migration survivorship. And
The
so
migrant. Okay. So that
yeah.
okay. Cool. Um, I had another more of a comment than a question, and then I'll let someone else speak because I think I saw Mark had his hand up. Your the Rogers Castro thing was a nice thing to use.
Uh-huh. Uh-huh.
But as you know, you can like pick a lot of different values for all the different parameters in the Rogers Castro model. And so
Right.
given you're sort of you're trying to see like how migration momentum sort of compares the scale of that compared to fertility,
Mhm.
I would also be curious to see like how much sensitivity there is to different values of those
Yeah.
Rogers-Castro parameters. Just so you get a sort of an idea of the magnitude. Like you mentioned before, that if you assume that all the migrants enter at the one age, it becomes quite
Mhm.
similar, more similar to the fertility case. But I
Mhm.
would also be curious, just from a sensitivity angle, like how much does the Rogers-Castro sort of shape matter? Because The one that you put on the screen seemed to have a lot of kids coming in. Like,
Yeah.
how you can sort of get different shapes of that weird double exponential thing. So
Mhm. Mhm.
anyway, just that was more of a suggestion maybe for when you submit this paper to the formal section of demographic research.
Yeah, no, thanks so much. I think that's a great suggestion.
Um, Mark, you've put your hand down, so maybe that means that you don't have a question anymore.
Well, I sort of thought I didn't, and then I saw this slide and I thought maybe I do, and then I heard your question and I thought maybe I didn't, and now I think I can maybe pull something out of the wreckage of what I was thinking earlier. Um, Thanks, Nick. That was an interesting talk. Let's see. My sort of rough understanding, and this might not be accurate anymore, is, and I think it's on here. So the effect of the age. So when you're talking about the momentum just with fertility, I think
Yeah.
the age pattern kind of just boiled down to mattering. Really, the only thing that seemed, I think, mattered about the age pattern was the mean age of childbirth, which is sort of supported by some of the stuff here. So with um, similar to Monica's question, is it possible to simplify the age pattern of migration in such a way? I mean, is there any kind of scenario or simplification under which you can kind of just distill that down into one or two kind of parameters, and that's all that matters in the long term?
Yeah, no, I think that's a great question. We've done a little bit of work on that. Like kind of mentioned earlier, we have this other case where like all migrants are arriving at say age 15. And if you do that, you can actually have this n of x term be like a delta function where it's like you only have like it's one at, 15, 0 everywhere else. And then you can reduce all of this a bit more. You can also like say, okay, here's what happens to the mean age of childbearing, or they're the same, or so on. And so then a lot of things simplify and you get this nicer expression. And so, in another world, I made the talk a lot more about that and maybe it was more interpretable. And so maybe I should have done that, but I was also really excited about sort of, I don't know, showing the whole thing and saying you can go all the way down. Um, and then this is what you have. But yeah, I think there's definitely a lot of value in thinking about, okay, like what happens if we take a simpler case and how can we, I don't know, think about reducing this. And like you're absolutely right that that helps with the interpretability. Yeah.
Okay, thanks.
Um, Thanks. I see Hampton's got his video on. Maybe that means he's got a question, but just one from the chat from Antonino first. Is do you think the analytical solution you show could be used for counterfactual projections to inform policy?
Um, I mean, I really hope so, but I think it's probably quite far from that right now. I think it really would take more of a dive into the policy literature, which I haven't done so much of right now. But if people, in this room have, I would love to hear insights, recommendations, and so on. So I think part of my and Josh's interest in this project was with an eye towards policy. And I mean, everyone knows there's so much kind of conversation and discourse around fertility rates, migration, and so on. And so I think being able to sort of have, I don't know, have some kind of contribution to this discussion in a policy context is definitely a goal, but I don't feel super confident that we're there. Um, yeah, I hope that answers it.
Thanks. Yeah. Hampton, and then Fernando, and then Mark.
I mostly wanted to appear to point out that Antonio did have questions in the chat. I
Oh,
am
that's you.
curious in the question to his sorry, the answer to his second question about whether it's a one sex or a two sex formulation.
Yeah. Um, so there's another question in the chat. I'm not sure if you can see the chat
Oh,
from your screen, but it's basically you're working with a one-sex population. Migration schedules are often really gendered. Have you considered any ways of incorporating gender?
short answer, no, but definitely something that is on the horizon. As I think we have all the sort of like machinery and formalism and capacity to sort of, project to handle gender separately and to sort of be more nuanced and like thoughtful about this. Um, But for the purpose of like this presentation, like I haven't shown you any of that, and we haven't really done that yet. But I think that's like a great suggestion and like definitely worth thinking about. Yeah.
Great. Fernando, then Mark.
I think you're. Oh, okay.
Okay. Just a couple of questions. First, on that curve, on the old age ratio that showed. So, don't you think that that is the expected behavior of the old age dependency ratio? Because at the end of the day, migration is basically theoretically and empirically has the very same impact as mortality. So when you're using that positive migration, in fact, you are giving initially a negative mortality impact in your population. That's why you have that decrease in the dependency ratio. Then you keep all schedules constant, correct?
Yes.
So at the very long term, that's what you'd expect. All populations will tend to stability. That is maybe I did not understand it correctly, but this is exactly what I would expect here. You have initially a negative mortality impact via migration. That's what we're doing here, because your net migration is positive. If you were to use this very same model with a negative migration schedule, net migration schedule, you'd invert that curve, right? You'd have a rise in old age dependency ratio because you are losing more people via migration. You are basically killing more people. And this is happening also because your net migration schedule has a lower mean age than the mean age of the population. If you use a mean age migration schedule with a mean age that's higher than the mean age of the population, even if it's negative, you are going to have an increase in old age dependency ratio.
Right. Okay.
Theoretically and empirically. I mean, so when I look at this figure, I would say, and why would you be surprised on it? Because that's exactly what I would expect. You have a negative mortality impact, and in the very, very long term, both populations tend to stability. Right?
Right.
Migration is exactly inverted or non-inverted mortality from a mathematical demography standpoint, right? It depends on at the end of the day, it depends on if it's net positive, net negative, and the age schedule, and the mean age of the age schedule, if it's below or above the population you work with. So if you keep this schedule and take another population and their age is below the migrant or above the migrant or vice versa, you are going to have different things here.
Right.
So first come to the BS, that's what I would expect. Maybe I got it wrong. I don't know. And my comment on mean age is also related to our points on mean age of childbearing and mean age of reproductive span, because you have to look at your population initial and their mean age, and as you evolve, how all these mean ages are moving here as they move to stability.
Right.
And the other point is also related to something Monica, I presume, said, and other colleagues on the chat, is that I know that everyone here would or could assume any fertility schedule in the very long term. You can assume that to be on the net zero. Women will start having 4 children on their during their whole lives, etc. But you cannot, or it's very difficult to assume the very same migration schedule on the very long term.
Yeah.
It's different.
Yeah.
So first you have, of course, a issue of source of migrants, right?
Yeah.
At some point, migrants will extinguish themselves if you have to feed any other population with a lot of migrants.
Yeah. Yeah.
And that this goes back to the absolute number someone asked about.
Right. Yeah.
So from a fertility or mortality or any other perspective, or fertility or mortality perspective, say, what will happen if I have this
Yeah.
fertility policy, childbearing policy, etc. But how can you expect to inform policies in the long term, assuming bottom line, I think that's not realistic to assume
Yeah.
any migration schedule, positive or negative, in the long term, even less in the very long term.
Yeah.
I don't know if I agree, but I heard you saying policy a lot of times during your presentation, so
Yeah.
that stuck with me.
Yeah. No,
Does this
thank
make
you.
sense?
Yeah, it definitely does. And I totally agree on this second point. I'll get to the first one after. But yeah, I agree it's totally unrealistic. And even assuming that fertility rates are going to stay constant is already unrealistic. And I totally take your point about even more so for migration. Um, and so I think, yeah, and kind of back to Antonino's question, I think for us wanting to maybe in some way, if indirectly be useful for policy, this is kind of a challenge. I think one thing that I'm sort of still thinking about is that even in the very short term, you have these like large effects. And so, I mean,
Mhm.
we're not answering what happens after that if you have a changing migration schedule, right? Um, but I think there's still, I don't know, I would hope and I'd like to think room for sort of drawing interesting insights out of this. Um, and the first point was about, oh, is this surprising? So I think for me, I think the reason this was maybe surprising to me was because I was thinking about these curves, how we see there's
Yeah.
differences in total population size, but we kind of see the same overall trajectory. And I'm
Mhm.
not super immersed in the migration literature. And to maybe someone who was, this wouldn't have been as surprising. But I think for that reason, I was quite surprised to see these like super divergent paths here. And also that there was
Okay.
this convergence in the long term, even if it is very unrealistic. Yeah. But thank you for,
Probably, no, and
yeah,
my question would be, you have this initial shock, what would happen if you remove the migrants,
right.
like
Yeah.
after
Interesting.
25 years?
Right.
So you have this initial, as you said, or you keep the migration schedule for 25 years, which I presume is around the bottom low of the shock, migration shock, so to
Uh,
speak. And then what if you remove that?
yeah.
What will happen with your momentum and with all the other age structure measures? I don't, just thinking.
Yeah. No,
Okay, thank you.
thank you.
Thanks, Fernando. We're kind of at time. So Mark, if you're quick, otherwise you can follow up via email. You're muted, so
Just well, okay. The quick thing would be careful with the term replacement migration. The population division made that mistake many years ago, and
Okay. Mhm.
it caused quite a lot of grief and continues to do
Okay.
so. Especially if you're going to start,
Yeah.
talking about policies or the implication for policy.
Okay. Thank you.
very good point. But I think we'll leave it there. Thanks everyone for joining today. Fabulous presentation, Nick. Thanks very much. I and Antonino will be at PAA wandering around with formal demography working group stickers. So if you see us and you would like a sticker, please come up and say hi. Otherwise, we'll see you all next time. Thanks very much. Thanks, Nick.
Okay. Thank you.
Bye.